Hello, welcome to another lecture on boundary theory. In this lecture, I am going to derive the Von-Karman momentum integral equation. Von-Karman momentum integral equation. It is also called MI equation, momentum integral equation. So this equation can be derived by integrating the Prandtl boundary equations. We have the Prandtl boundary equation, the continuity dou u by dou x plus dou v by dou y is equal to 0, and u dou u by dou x plus v dou u by dou y is equal to, in terms of potential flow velocity gradient, like this, mu into dou squared u by dou y squared. So, and basically what we do is this equation is integrated uh, over the height of the boundary. At a particular x, you choose a particular x. You take a particular x on the, this is the distance along the body surface, and this is the distance normal to the body surface, and that is denoted as y. So we have the boundary layer schematically represented like this. So we go to a particular x and integrate from y is equal to 0 to y is equal to delta, y is equal to delta on this equation. And of course, we may have to do the integration of the continuity equation also for simplifications. So we have that integral from 0 to delta u dou u by dou x dy plus integral 0 to delta v dou u by dou y dy is equal to integral du by dx dy plus integral 0 to delta mu dou squared u by dou y squared dy. So basically, momentum integral equation is this equation. This equation will give the integral expression over the board layer. So that can be applied for anywhere, any particular x. So all along the x, we have an equation of this sort for the board layer. But this equation is called momentum integral equation. So now we have to do some mathematical simplification. Just only mathematics is remaining to be done for arranging the momentum integral equation in a form that is given by Von-Karman. So basically, what we do, okay, there are certain terms which we can integrate. So this can be directly integrated. This can be directly integrated. But this is differentiation on x, and integration is along y dash. So direct integration is not possible. So this x differentiation will keep as it is. Y differentiation and integration we will do. Okay, this is actually v into something, some other function. This v is one function, and dou u by dou y is another function of x and y, and that we are integrating along the y direction. So okay, this we will keep as it is 0 to delta u dou u by dou x dy. So this is product, can be integration can be done by parts. First function into integral of the second. So v into integral of the second is dou u by dou y dy integral, and this differentiation and integration, right? So it comes to u, and apply the limit y is equal to 0 delta minus integral of 0 to delta differential of the first, what is dou v by dou y, differentiation with respect to y, and integral of the second, what is the integral of the second, that is u. So this is So integration by parts gives that. So integral 0 to delta capital U du by dx dy. And this is also direct, that gives nu into two differentiations, that is second order differential, so that becomes dou u by dou y. That is apply the limit between y is equal to 0 and delta, and then this mu can be written as mu by rho. So that way we can write that in terms of skin friction drag, skin friction shear stress, skin friction shear stress. Okay, now this simply we repeat 0 to delta u dou u by dou x dy, plus we apply the limit, that is v delta v at delta u at delta, minus lower limit v at 0, v at y is equal to 0, v at y is equal to 0, v at y is equal to 0, u at y is equal to 0. So I'm not writing the x y value. So we know by no slip condition these two things. So u at y equal to 0 and v at y equal to 0, u is equal to 0, v is equal to 0. So these two are 0, equal to 0. And what is u delta? U delta is the value of u at delta, that is the potential flow velocity. So this u delta becomes equal to capital U, capital U. Okay, that's this capital U. Okay, v delta will get an expression for v delta. And then this term is there, minus integral 0 to delta. Okay, dou v by dou y, and this product is there, we cannot do anything. Actually, we have done integration by parts. Integration by parts is done. So dou v by dou y, by continuity equation, dou v by dou y is equal to minus dou u by dou x. So there's a negative sign and dou u by dou x. So the negative sign over there, that makes this one positive, and dou v by dou y is dou u by dou x into this u dy. So this is equal to integral 0 to delta capital U capital du by dx dy, plus dou u by dou y at delta. U remains same. So dou u by dou y at y is equal to delta is 0. So we can take the upper limit mu by rho into 0, minus lower limit is dou u by dou y at y is equal to 0. So I will copy this. So what will happen is this will go, this is going, and something for v delta. So v delta is mathematically v delta is integral dou v by dou y from 0 to delta dy. Actually, that is b. This is actually, if I do this, okay, I will check this. If I do this kind of this thing, I will get b y is equal to 0. That is v delta minus v at 0. So v at 0 is equal to 0 because of no slip. So this is equal to v delta. So instead of v delta, we can substitute this one. This one is equal. So that if I do, so that's a capital U there. That's a capital U there, and then integral 0 to delta dou v by dou y dy. Okay. Okay. Further, one more thing I can do is This is V delta. This is V delta. V delta is this. V delta is this. And again, I'll use the continuity equation to write in terms of minus dou u by dou x. So minus integral 0 to delta. This is dou u by dou x dy. Okay, that I substitute here. So that it will be simplified properly. So we use for all these are the these we do not want the v in the momentum integral equation. So all these will be replaced by u. So dou v by dou y is replaced by minus dou u by dou x. So I'm having dou u by dou x dy, and there's a negative sign, and that will make this one negative. So I will shift this a little bit to this side. The minus and the so we get into this kind of form. This is just we are doing this mathematical simplification, and thereby we get the momentum equation. So, okay. Now look at this. There is one u dou u by dou x, another u dou u by dou x. So, integral 0 to delta 1 plus 1, 2u dou u by dou x minus this is something. Okay, this is something u into integral 0 to delta dou u by dou x dy. Okay. This is equal to, okay, this also I'll take it to the left hand side and write it as minus integral 0 to delta capital U capital D. And this is on the right hand side. On the right hand side, I have this is equal to there's a minus is there, minus 1 by rho mu into dou u by dou y at y is equal to 0. And this is what is called the wall shear stress, toe load. So this is wall shear stress. And we'll make one more simplification. 2u dou u by dou x is this 2u dou u by dou x is integral 0 to delta of dou by dou x of u squared minus u into integral 0 to delta dou u by dou x dy minus integral 0 to delta capital U du by dy is equal to minus rho naught by rho. And this is now, this is du by dx. So that's right. If it is y, we can do that integration. That's what is dx. Now the thing is that we are having differentiation on x. So the whatever steps we have carried out so far on these Prandtl boundary equations or the momentum equation is to convert all small v's into u's and all differentiation in terms of x rather than y. And during that process, some integration, we could do some integration, and finally to lead to this kind of an equation wherein the right hand side is the wall shear stress by density. So this form we got. Now one important mathematical simplification we will do, one mathematical simplification. So here one step remaining, mathematical step remaining is this is integration is done outside. Here integration is done second and differentiation is done first. So first differentiation and second integration. And I want to write the differential of integral quantities. That is, differential is out and integral is inside. So we have integral quantities like momentum thickness, displacement thickness, etc. The differential of momentum thickness, that form I want to write. So differentiation has to be outside. So it is called changing the order of differentiation and integration. So for that we will use one important theorem in mathematics, that is called a Leibniz theorem. Leibniz theorem. So there is an important theorem in Leibniz that's called the Leibniz theorem. Suppose I have a function of x, y. I am doing integration with respect to y and applying some limit on y is equal to some function of x and to another function of x. So upper limit and lower limit. So once this integration is done and limit is applied, the total expression would be a function of x only. So that I can do the d by dx. So this is an integral expression finally leading to a function of x which can be totally differentiated with respect to x. So here in this particular exercise we are having some integral quantities like momentum thickness, displacement thickness, etc. So for that I can do differentiation along the x in a total differentiation. Okay. So for that and this okay this actually differentiation is done. Differentiation is there for this integral as well as the limit. So first we do the differentiation on this differentiation on the differentiation is on the limits d by dx. And d by dx of integral without limit, if you do, this is a function of xy dy. So that will lead to function itself evaluated at the upper limit. So it will be f of x comma b of x. And lower limit will have a negative sign. So it will be dA by dx. F of x evaluated at the lower limit. Plus, okay, plus these are boundary values, boundary values. Plus, so integration is there from a to b. Okay, then differentiation we are doing on this with respect to x. This is a function of x and y. So the differentiation is dou by dou x of f of x, y. So this is called the Leibniz theorem, and its mathematical proof is also possible. That way, this is called Leibniz theorem. Okay. And now that we are having terms like this, I want to make into terms like this. So here differentiation is inside, integration is outside. I want to make integration inside and differentiation outside. So such a term is what is here. So that we will write this d by dx of integral 0 to delta u squared dy. Uh, that is this term. So I am having this term. So this will be subtracted, and this will be added. And what is subtracted now? Minus this delta of x. So d delta by dx into the function u squared evaluated at delta. U squared evaluated at delta. What is u at delta is equal to capital U. So u squared evaluated at delta will be capital U squared. So okay. Uh, Similarly, okay. Now for the lower limit, what happens? Lower limit is 0. Lower limit is 0 and is not a function of x. And so dA by dx will be 0, so this will not contribute. So the same thing for this also. So we are having, we can take d by dx. Okay, u is anyway, it's outside. Capital U is anyway, it's outside. Then d by dx of integral 0 to delta u dy. And this minus will come, this because of this minus it will become positive. That u is always there, so u is something is a common, so u is there, and d delta by dx, and this u evaluated at delta, that is going to be capital. So we get like that. So you apply Leibniz rule to simplify, to change the order of integration between the outer and okay, outer changing the order of integration and differentiation. Okay, that will be there. So now that we have finished with this one we have finished. Okay, minus this term minus integral 0 to delta du by dx dy is equal to minus rho dot by rho. I will copy this. This is actually a 6 delta. Okay. Now that d delta by dx u squared minus and plus u squared d delta by dx. So these we cancel. So we are having d by dx of integral 0 to delta u squared dy minus u into d by dx of integral 0 to delta u dy minus integral 0 to delta capital U du by dx dy is equal to minus 1 and this is that. Okay. Now I will do one more thing is that this u is outside d by dx. I'll keep it inside. So d by dx of integral 0 to delta u square dy minus d by dx of u is either placed here or inside is okay because this capital is not a function of y. So integral 0 to delta u into capital U dy. So that means the integration differentiation is done on product actually, and d by dx of u is taken outside and differentiation is done, that is this term. But I have an additional term in this because of the differentiation on u. So this is negative, this is negative, so we'll have something added. So that is du by dx into integral 0 to delta u dy. So differentiation of u in extra term is there with this taken constant. So without differentiation. So this will make these two terms together will bring this term. So then minus integral 0 to delta capital U du by dx dy is equal to minus this almost we have reached. Now this d by dx and this d by dx will combine. D by dx is combined 0 to delta u squared minus u capital U into capital U dy and that is finished. So now that this du by dx is not a function of y, so I can take it outside. Even capital U is not a function, that also can be taken outside. So du by dx can be taken outside. So du by dx is taken outside, and there is an integral 0 to delta u minus capital U dy is equal to minus 1 and this is d by dx of integral 0 to delta and small u is taken outside u minus capital U dy plus d capital U by dx not okay plus only plus integral 0 to delta u minus capital U dy is equal to minus rho naught by rho. So if you look at closely, we have something like the momentum thickness delta 2 is equal to integral 0 to delta and u by capital U 1 minus capital U by U dy. This is delta and capital sorry, small u by u by u into 1 minus small u by capital U. So that is a capital U, or you can write, and there is something like U squared. So one U squared can be multiplied. So that this U will go, this U will go. One U is multiplied inside, that will make this, and this is so this is like this. This is like this. Or here U minus U. This is capital. This is capital. This is the reverse. So I can put negative sign and put this as small u minus capital. Small u minus capital. So that way we can make that way. This can be, this can be, this can be, this can be. D by dx of minus u squared delta t. That is everything, plus du by dx into this. If you look, it is it is displacement thickness. This is actually displacement thickness into u into displacement thickness delta 1 is equal to minus 1. So, so this is what is called the one form of momentum integral equation. One form of momentum integral equation. Okay, the negative sign everywhere. There's a negative sign is there. That can be changed. Everywhere there's a negative sign. Okay, here also there's negative. Here there's a negative. Here also this is also minus delta one, minus delta. So minus u delta. So that way, this is also minus u delta one. Here there's every term has a negative sign. So this will be this will be. So it can be written in a more compact manner. D by dx of u squared delta t plus du by dx capital U delta 1 is equal to total. This is called the momentum integral equation. And the delta 2 is, what is delta 2 is the what is delta 2 is the momentum thickness, that is integral 0 to delta, or also it may infinity u by capital U into 1 minus u by capital U dy, and delta 1 is integral 0 to delta, integral 0 to delta 1 minus u by capital U dy. So these are the equations. This is called Von-Karman momentum integral equation. Momentum integral equation, or MI equation, can be called as MI equation. In another form also it can be written. It can be written in some different form. This product of these two can be done differentiation. That way we can write this again. Simplify as the 2u du by dx delta 2 plus u squared into d delta 2 by dx plus du by dx u delta 1. You can throw it by that way you can write. So by this can write first u squared to d delta 2 by dx plus that's a du by dx common is there. Du by dx common into 2u delta 2 delta 2 plus delta 1 into u, and this u also can be taken outside. So u into 2 delta 2 equal to 1 for a flat plate. Capital U is equal to u infinity is a constant. So du by dx is equal to du infinity by dx is equal to 0. this entire thing will vanish. So we get d squared d delta 2 by dx equals to 1 by 12, or d delta 2 by dx. So that is the derivative of the momentum thickness along the x direction is equal to 1 by rho squared, or that u can be written as u infinity. So this is for a flat plate. This simplified momentum in the equation is applicable. This is somewhat more general. This is somewhat more general. This is somewhat more general for modular with the pressure gradient. Uh, pressure gradient. So with the pressure gradient. So we will stop this particular lecture.